In episode 2, the softmax function gave us a correct verdict. Blue won with 86% confidence, but the model does not start out correct. Training begins with random weights, where the model is almost always wrong. Consider a different prediction from an earlier training step. Green is assigned 80% of the probability mass. The ground truth is blue. This overconfident wrong prediction is exactly what a cost function is designed to quantify and correct. This incorrect confidence is not just a mistake, it is a measurable state of high mathematical energy, a location in a vast, high-dimensional space. This is the loss landscape, a terrain generated by our cost function. Every point on this surface represents a different configuration of the model's weights. Height equals error. The red peaks represent catastrophic failure. The deep blue valleys are the ground truth. Our goal is to find the lowest point. This white sphere is our model. Its current weights place it stranded at high altitude, deep in the red high error region. The cost function j of theta calculates the exact penalty for our bad prediction. This is cross-entropy loss. It uses logarithms to turn an overconfident wrong answer into an astronomically high penalty. To escape the peak, we calculate the gradient, a vector that points in the direction of steepest ascent at our current location. This is the red arrow. The gradient tells us which way is uphill. The gradient is the combination of two partial derivatives. This teal component tells us the slope along weight 1, how much the loss changes when we nudge that single parameter. This orange component tells us the same for weight 2. Together they form the full 3D arrow pointing uphill. The gradient points uphill toward maximum pain. To optimize, we negate it. We step in the exact opposite direction. This is the core update rule of gradient descent. Before we watch the descent, a critical question. Why cross-entropy and not standard mean squared error? The answer is the terrain it creates. With squared error, confident wrong predictions sit on vast, flat plateaus. This ball has almost no gradient to follow. It sits there, barely moving. Cross-entropy uses logarithms to warp that flat terrain into steep cliffs. The ball rolls immediately and strongly. The more wrong the model is, the faster it descends. The distance we step along the negative gradient is controlled by the learning rate eta. Get it wrong and the model either freezes or explodes. If eta is tiny, the descent is painfully slow. The model updates, recalculates, and inches forward. After many steps, it is still far from the minimum, frozen in the landscape, making no visible progress. Now increase eta aggressively. The ball leaps over the valley entirely, landing on the opposite slope. Then it overcompensates back. The mathematical pain actually increases. We are bouncing across the surface, never converging. But the landscape is not a set of discrete cliffs. It is a continuous field of forces pulling the model toward the minimum at every single point simultaneously. Every arrow on this surface points downhill, toward the lowest blue valley. Modern optimizers do not jump, they roll. They treat the gradient as physical acceleration, not a step size. The model becomes a glass sphere sliding under the laws of physics. By incorporating momentum, the ball gains kinetic energy on the steep cliffs. It uses this accumulated speed to punch straight through the shallow local trap that previously stopped us. Even when the gradient signal weakens, momentum carries the sphere forward to the global minimum. At the global minimum, the sphere does not stop instantly. It oscillates, each swing smaller than the last. Finally, the energy dissipates. The sphere settles at the absolute bottom, in the deepest blue valley. The cost is minimized. The internal weights of the model have physically shifted. The error is resolved. Let us return to the output layer and see what this minimization actually looks like. We return to the output layer. The logits are recalculated with the new optimized weights. The misplaced confidence in the wrong answer vanishes. The probability mass shifts entirely to the ground truth. The model now correctly predicts the word blue. One full optimization cycle is complete. Gradient descent only works if you already have the gradient. But our model doesn't have one parameter. It has billions arranged in deep sequential layers. To calculate the error, data must travel forward through every weight matrix layer by layer. Each set of connections carries the signal forward. This is forward propagation. But how does a parameter buried 50 layers deep know which way is downhill? The error signal must flow in reverse, backward through every weight matrix. At each step, the partial derivative of the final cost is calculated with respect to that layer's output. This requires the chain rule. This backward flow of gradients is backpropagation. Gradient descent guided by the cost function is how every neural network learns, but we only scratch the surface. In episode 4, we tear open the backward pass and follow the chain rule as it distributes responsibility for every wrong prediction across billions of parameters. Subscribe to Fromobius. Let us decode the black box together.